Overexplain presents How to Write Epsilon Delta Proofs. Oh, the dreaded and feared epsilon delta proofs. Many a first semester calculus student has found themselves stumped by them, but I'm here to help. The goal of this video is to show you how to write simple epsilon delta proofs of limits using the formal definition. If you need a better understanding of the formal definition of limits using epsilons and deltas, see my other video, the epsilon delta definition of limits. So let's look at this example. Use the epsilon delta definition of a limit to prove that the limit as x goes to 5 of 1/5 x minus 2 equals negative 1. You can see the graph of the function here, and you can see that the limit as x goes to 5 looks like it is negative 1. So let's remind ourselves of the definition. Let f be a function defined on an open interval containing c, except possibly at c, and let L be a real number. The statement the limit as x goes to c of f of x equals L means that for each epsilon greater than 0, there exists a delta greater than 0, such that if the distance that x is from c is less than delta, then the distance the function value is from the limit is less than epsilon. So looking at the definition and then at our specific example, we see that in our example, c equals 5, the function f of x equals 1/5 x minus 2, and the limit is negative 1. And looking at our function, we see that it's a line with slope of 1/5 and a y-intercept of negative 2. Now, we know that the limit of a continuous function is just the value of the function at that point. So, since f of 5 equals negative 1, we know that that is indeed the limit. Now, someone might wonder, if we know the limit of a continuous function is the value at that point, why do we need to prove it now? Well, we know that fact because someone proved it before. And you're at your university because we are trying to train up a new generation of mathematicians. So we're starting with simple examples of proofs, so you can understand how it's done. The more difficult examples will be left to the mathematics professionals, or at least the math majors in the more difficult classes. So, how do we prove this? The basic idea is that we need to show that delta exists. How do we show delta exists, you might ask? Well, first let's look at an example not related to math. What if the evil villain, Professor Ulesh, had created a divide by zero machine and was going to use it to blow up the world, unless Mathman comes to stop him. But in order to stop him, he needs a key to get into the warehouse where the machine is. But Professor Ulesh has the only one. Or does he? How could you prove that another key exists? Well, you could just produce it and show it to him.
Oh, here it is.
So that's the idea with delta. We need to produce one and show it. Let's see what that would look like with a specific example first. So let's let epsilon equal 0.5. What does that mean? That means for the delta we come up with, all the x values within delta of c, which is 5 in this case, must produce function values that fit within 0.5 of the limit value. Our limit is negative 1, so our upper bound would be negative 1 plus 0.5, or negative 0.5, and our lower bound would be negative 1 minus 0.5, or negative 1.5. So how do we find the x values that go with this? Let's do some algebra. If the boundary of the function values is between negative 0.5 and negative 1.5, then we set the function equal to those values and solve. So we would have f of x equals 1/5 x minus 2 would equal the upper bound, negative 0.5, and we would have that the function 1/5 x minus 2 equals the lower bound, which is negative 1.5. So solving the first one, we would add 2 to both sides and multiply by 5. And we get that x equals 7.5. And for the lower bounds, we would again add 2 and multiply by 5 and get 2.5. So now we can see that our x values align with the graph. And if we would subtract from our c value 5, we would find that delta equals 2.5. But what about other epsilons? How do we find the delta for any epsilon we could choose? The answer is we do the math with the variables epsilon and delta. So, no matter which epsilon we choose, we get that the upper and lower boundaries are -1 plus epsilon and -1 minus epsilon. And now we will put the x values in terms of delta. So, here our x value is delta more than 5, so 5 plus delta. If we put that into the function, we get that f of 5 plus delta would equal, in this case, the upper bounds, -1 plus epsilon. So here we have put 5 plus delta into the function, and we get 1/5 times 5 plus delta minus 2. And now we need to solve for delta. So here's what we need to solve. All right, we're going to distribute that 1/5. 1/5 times 5 plus 1/5 times delta. And so we get 1 plus 1/5 delta minus 2. And then we're going to add 1 to both sides. So the 1 minus 2 was -1. Adding 1 to both sides gives us 0 on both sides. And then to get rid of the 1/5 multiplied by delta, we're going to multiply by 5 on both sides. So our delta equals 5 epsilon. Now we could do this for the other side as well. That is, for -1 minus epsilon. So the x value would be 5 minus delta. And when we put that into the function, that would be equal to the lower bounds in this case, -1 minus epsilon. So putting that into the equation, this is what we need to solve. Let's solve it. Again, same thing, except we have a minus instead of a plus. So we have a -1/5 delta equals 0 minus epsilon. Oh, but we have a minus epsilon, so we're going to get that delta equals 5 epsilon. And we see that it's the same as before. In fact, because we're dealing with a linear function, part of the definition of which is that it always grows or shrinks at the same rate, the results with c plus delta and c minus delta would always be the same. So with linear functions, we only need to do it for one. So we saw that when epsilon was 0.5, delta was 2.5. And then we showed algebraically that for any epsilon, delta would just be 5 times whatever epsilon you give me. What this means is, if someone would say, here's an epsilon, 0.00003, then I would say, okay, there's a delta, and it's 5 times 0.00003. So the delta is 0.00015. Or if I give you an epsilon, 0.0018, then the delta for this would be 5 times that, or 0.09. So we have that whatever epsilon you give me, the number that is 5 times it also exists, and so that can be our delta. Now, once we come up with a delta, we have one more step before writing the proof. We need to take what the definition says and make it work with our delta and epsilon. We need to start with this and then get to this. Meaning, we need to get from here to here. In order to do this, I find it easier to work backwards. We start with the function minus the limit is less than epsilon. Then let's plug in the function, do the subtraction, and then let's look back at where we need to go. We need, instead of 1/5, 1, and instead of 1, 5. So we can multiply both sides by 5. And that gives us that x minus 5 is less than 5 epsilon, which is what we said that delta was. Now, to write the proof. Remember how I said the easiest way to show something exists is just to produce it? Well, it's slightly more complicated than that.
Knew it.
So, going back to the example earlier, suppose, since the fate of the world is hanging in the balance, that once you show Mathman the key, he's not quite sure it's actually the right key. His entire plan depends on having the right key, after all. So you have to do more. You have to show him that the key actually works to open the lock before he will believe you. And that's what we need to do in our proofs. We need to produce the delta, but also show that it works. So here we go. Suppose that f of x equals 1/5 x minus 2. Now let epsilon be greater than 0, and now we produce our delta, and let delta be equal to 5 times epsilon. Then we need to show this. We need to show that the absolute value of x minus c being less than delta also implies that the function minus the limit is less than epsilon. And we just did that algebraically, so we just need to copy and paste what we did before. So we'll say, then, if the absolute value of x minus 5 is less than delta, and then we do some algebra again. Just putting in a 1 for clarity, and we're replacing delta with what we said delta equals, which is 5 epsilon. Now we're going to factor out a 5. If this confuses you, just go ahead and multiply the 5 back in and you'll see that it works. Now we can divide by 5 on both sides. Now we need to get to the function minus the limit. So this is the function, and we see that we have a minus 1 instead of a minus 2, but we also need to subtract the limit in there. So what we're going to do, and looking back at the algebra helps us a little bit. We can look back and see what we did. What we're going to have to do is replace that negative 1 by a minus 2 plus 1. Work out the math. It's the same thing. We didn't do anything to both sides. We just rewrote the negative 1, put in a few parentheses, which is allowed. And now we need minus the limit. The limit was negative 1, so we realize that. We can just write the plus 1 as minus negative 1, and then the 1/5 x minus 2 is the function. So we have the function minus negative 1 being less than epsilon, and that's what we needed to show. We're going to write that out. So there exists a delta greater than 0, delta being 5 times whatever epsilon you give me, so that if the absolute value of x minus 5 is less than delta, then the absolute value of the function minus the limit is less than epsilon. Therefore, the limit as x goes to 5 of 1/5 x minus 2 equals negative 1, according to the definition of the limit. Okay, now I understand that all that was a lot, so let's do the same thing, but with a different limit to prove. So here's a new example. Prove that the limit as x goes to 0 of 5 minus 3x equals 5. So first, let's note that c in this example equals 0, and that the limit equals 5. Now we're looking at the function 5 minus 3x as x gets really close to 0. Obviously, since this is a continuous function, the limit is just the value of the function at 0, which is 5. But how can we prove this using the formal epsilon delta definition? Again, we're doing a simple example to show the principles of how our forefathers who invented or discovered calculus proved limits. The more complicated proofs are beyond the scope of Calculus 1 and would be taught in the class Real Analysis if you're interested. So here's our function. It is a line with slope of -3 and y-intercept of 5. Now let's zoom in a little and choose a positive number epsilon. What about epsilon equals 0.3? Then the range of values for the function would be 5 minus 0.3 and 5 plus 0.3. Now, what x values will give us a function value of 4.7 and 5.3? Let's do the math. So we set the function equal to the y value and solve for x. So let's do the lower bounds, that's 4.7. We're going to subtract 5 from both sides and divide by -3. And so x would equal 0.1. And now we'll set the function equal to 5.3 and solve again. Subtract 5, divide by -3, and we get -0.1. So our x values are 0.1 and -0.1. So our delta value would be the distance these numbers are from c, which is 0, and the distance is 0.1. If we are given that epsilon equals 0.3, then delta could equal 0.1. but it could also equal many other values as well, specifically anything less than 0.1. But we're going to use 0.1 as our delta. So then, if the absolute value of x minus 0 is less than 0.1, then the absolute value of the function minus 5 would be less than 0.3. So, given any epsilon, how does delta relate in this example? Let's do the algebra as before. So, if we use a generic epsilon, then we're looking at boundaries of our limit plus and minus epsilon. So, we have 5 plus epsilon and 5 minus epsilon. As before, we only need one, so let's choose the plus epsilon. So here, the x value corresponds to c minus delta since we have a negative slope. Our c in this case is 0, so we're going to put in 0 minus delta in for x in our function. So let's do the algebra. So we need to put c minus delta into the function and set it equal to the limit plus epsilon. Then putting in our 0 for c and our 5 for L, we get f of 0 minus delta equals 5 plus epsilon. So we're going to put that into the function, 5 minus 3 times 0 minus delta. We get 5 plus epsilon. We're going to do a little simplifying. We would get that 5 plus 3 delta equals 5 plus epsilon. Subtract a 5 from both sides, divide by 3, and we get that delta equals epsilon divided by 3. Now we do the algebra again. In order to prove this limit, we need to show that if the absolute value of x minus c is less than delta, then the function minus the limit is less than epsilon. So, working backwards again, we plug in the function and the limit. The function is 5 minus 3x, the limit is 5. We need to do some simplifying. 5 minus 5 is 0. We're going to factor out a positive 3 on the left-hand side. We can do this with absolute values. Now we're going to divide both sides by that positive 3. And we know that the absolute value of the opposite of x is the same as the absolute value of x, so we can replace that. Now we're moving it down a little for more room. The final step is to put in our c value. Well, lo and behold, that's 0. Not too hard. And we get, since delta is equal to epsilon divided by 3, we get x minus 0 is less than delta. So we'll copy this into the proof in just a second. So let's write the proof. You can always start out the same way. Let epsilon be greater than 0. Then there exists a delta, and you say what the delta is. In this case, epsilon divided by 3. And then we show that it works, such that whenever x minus 0 is less than delta, and then we're just going to copy what we just did, then x minus 0 is less than epsilon divided by 3. We can take out the minus 0. We can change the absolute value of x to the absolute value opposite of x. We can multiply both sides by positive 3 and put that in the absolute value. We can write 0 as 5 minus 5 and put that before and after. Then we have the function 5 minus 3x minus the limit, which is 5, being less than epsilon, and therefore we've proved it. Therefore, the limit as x goes to 0 of 5 minus 3x is 5. So, in summary, to write an epsilon delta proof for a linear or other simple function, here are some steps. First, put x plus delta, or x minus delta, depending on whether your slope is positive or negative, into the function and set it equal to the limit plus epsilon. Solve for delta in terms of epsilon. Then use algebra to get from the absolute value of x minus c is less than delta to the absolute value of the function minus the limit being less than epsilon, using the relationship of epsilon and delta you just found, and working backwards if necessary. Then write the proof presenting your delta, showing that the distance between x and your c value being less than delta would mean that the distance between the function and the limit is less than epsilon. Now, writing the proof of more complicated functions, such as the quadratic one I showed in the epsilon delta definition video, is much more complicated. If you're curious to see it, let me know in the comments, and maybe I can do that in another video. And there you have it, how to write epsilon delta proofs for linear functions. I hope this video has helped you to understand and to be able to conquer those epsilon delta proofs.